is Generalized Linear Models with examples in R, and we are on the very last question of Chapter 4, question 4.10. And what we're going to show here is that for a normal distribution, or using normal linear regression would be a better way of saying this, the expression for the AIC given here, so -2 times the log likelihood, I'll explain what all that means, but the log likelihood plus the penalty term, which is 2 times the number of unknown parameters, okay, is equal to the expression we saw earlier, like in chapter 2 or something, I think, okay, after we do something which is to ignore all the constants. And until you start working through this last bit here, it's hard to place exactly what they mean. So I just had to push forward until I could recognize when I needed to do that. So again, what we're going to show is that this expression for the AIC is equal to this expression up to some additive constant, and that will make more sense as we go along here. Okay, so let's try to simplify the problem. And the first thing to notice here is that 2 times the number of unknown parameters, that is 2p prime. Okay, so in other words, this part of the first expression for AIC is equal to this. Okay, so we really just need to focus on this piece here and this piece here. Okay. All right. So the way that I approached this was first to get an expression for the log likelihood when we are parameterizing the mu parameter to include some predictor variables. Okay, and so we did that starting, I think, in question 4.7, where we went through some particular steps here in 4.70b. Okay, and then did again in 4.8 and 4.9, I think, or something like that. And so I'll let you rewatch those videos, just where I go through the steps in a little bit more depth and detail. But the important thing here is that the log likelihood comes out to be, sorry, I have a cough, I may have to pause once in a while here. The log likelihood comes out to be this right here. Okay, so actually, let me start from here. So we get a log likelihood that looks like this, where we are reparameterizing the mu parameter to be the predictor variables times whatever set of parameters. Okay, so I'm illustrating or demonstrating or representing that like that. And then notice that this expression right here is the residual sum of squares. Okay, so we get that. Okay, and the fact that that the log likelihood for the normal distribution contains the residual sum of squares is promising, because we're trying to do things between the log likelihood and the residual sum of squares. So it's nice that we're already seeing some evidence that we're going in the right direction. Okay. So if we were to solve for the betas, or in other words, get the maximum likelihood estimates for the betas, then we would replace the betas here with beta hat, and also the sigma squares would become the estimate for that. But so then we could rewrite our log likelihood like this. Okay. Okay. Now also notice that sigma hat is the residual sum of squares divided by n. That is our estimate for sigma hat. So that means that I can plug this in whenever I see a sigma hat squared. Okay. And so I do that for this term over here, but not for here, just for ease of notation for a little bit here. But eventually we will switch this to the RSS divided by n. It just gets a little bit muddy. Okay. But anyway, so we have the log likelihood, and now we have our new expression for the log likelihood. Okay. Again, just by substituting RSS divided by n for anywhere where we see sigma hat, or some places where we see sigma hat. Okay. So we see it here in the denominator. So it goes down here. Well, now the RSS's cancel out, and we get n over 2. And so now our expression can look like this. Okay. And so now let's, now that we have a log likelihood function that we can work with, let's plug it into the AIC expression, which is -2 times the log likelihood plus 2 times the number of unknown parameters. Okay, so we have -2 here times the log likelihood plus the number of unknown parameters. Okay, and now I'm just separating these parenthetical terms out just to make the arithmetic easier to see. Okay, so we distribute the -2 over the two terms. The -2 cancels out with this -2 in the first one, so that just becomes n times the log of 2 pi sigma squared. And then similarly here, the -2 cancels out with this -2, and we're just left with n. And we have, oh, that should be 2p prime. Oops. Let me correct this. Okay. Oh, I missed one. Let me try that one more time. Okay. And so now we're going to bring back the expression sigma squared hat is RSS over n. Okay. And so we get, where are we here? We're replacing this with this. Now I realize that I have forgot to put a hat on these sigmas. I'll do that after the video here. But these are all sigma hat squared. Okay. That's fine. So now we have this expression. And so I'm just going to, when I have the logarithm of a product, here I have 2 pi times this guy. I can break that out into two different things. So I'm going to distribute the n, and I get this right here. And now this is the kind of ill-defined step where if we drop the constants from the AIC for up here, okay, that means that we're going to drop, that's a constant, and this n is a constant, okay? The 2p prime we don't touch because we're just dropping the constants of the log likelihood, okay, and the 2p prime is not part of the log likelihood. And so then we get up to some additive constant that, which is what we dropped, okay? We get that the AIC as per this expression equals this expression, which is exactly what we were meant to show. That is expression, what is it? That is expression 2 point, whatever it says up here, 2.35, okay? So I guess we will call that good, and we'll be moving on to chapter 5.